In this video, I'd like to talk about writing functions with exponential decay. So we're going to be looking at several different word problems that all feature exponential decay. And let's just jump right in, and we can come up with a strategy for how to approach these problems as we go. So at the moment, a hot iron rod is plunged into freezing water. The difference between the rods and the water's temperatures is 100 degrees Celsius. This causes the iron to cool and the temperature difference drops by 60% every second. Write a function that gives the temperature difference in degrees Celsius, which we'll call d of t seconds after the rod was plunged into the water. So we need to come up with a formula here for this function. And a general piece of advice when dealing with word problems is that if you're going to be using variables, it's a good idea to start by defining those variables, just so that you can write these in your own words and get a better feeling for them. So let's make just a little bit of room, and we need to define our function d of t and its independent variable t. Now t usually stands for time, not always, but in this case it does. So t is time, and it's also important to recognize the units. So in this case, the units are seconds. And then d of t, that is the temperature difference. So d for difference in temperature, and the units for that are in degrees Celsius. So we can write this. This is the difference in temperature, and that's between the water and the iron rod. And again, those units are going to be in degrees Celsius. So once you have the variables defined, then you want to go back and find key pieces of information that we can use to create the formula. And since we know this is an exponential decay formula, and you can tell that because we're dropping by a certain percent every unit of time, or every second in this case. So the general formula for exponential growth or decay, let's say we have some function f of t. This will be equal to a, which is our starting value, multiplied by our base raised to the t power. So a, that's the starting value. Since if you plug in t equals 0, notice that you get b to the 0, which is 1 multiplied by a. So 1 times a is, of course, a. And b, that's what we call our base. And since all of these problems are going to be dealing with decay, this is our decay rate, how much it's dropping by from 1 second to the next. And we're given key pieces of information here. We're told that the moment the iron rod is plunged into the freezing water, the temperature difference, or the difference between the rods and the water's temperature, is 100 degrees Celsius. So we're told our starting value. That is 100 degrees Celsius. Or in other words, if we want to use our notation here, when we plug in 0 to our function d, we just get back 100 degrees Celsius. And our base, that's our decay rate, that's the amount that it's dropping by every second. And notice they tell us that as well. It's dropping by 60% every second. Now, with decay rates, we have to be a little bit careful, since we're taking the original amount, or the amount that you currently have, and then subtracting 60% from that. So our base, this decay rate, which we call b, we take our original amount, or the amount that is currently present, and then we subtract 60% from that. So if we convert these to decimals, 100%, that's 100 divided by 100, that's just 1. And 60% is 60 over 100, or 0.6. So our decay rate, when we subtract this, is actually 0.4. Or in other words, from 1 second to the next, we're going to be multiplying by 0.4. So for instance, if we were to make a table here, let's just do this quickly for this problem. We know that when t is equal to 0, that our temperature difference is 100. But when t is equal to 1, we're going to be multiplying by 0.4. So 100 times 0.4, that is just 40. And you can see that a 60% drop from 100 would drop it 60 degrees. So 40 does make sense in that case. And you can continue this table if we go 1 second further. You take 40 and multiply that by 0.4, and you'll get 16 degrees after that second. And to continue on, every step, you're just going to be multiplying by 0.4. So we found our base and we found our starting value, so we can just apply those to this general formula here. So our function, d of t, it's our starting value, which is 100, and we're multiplying it by our base, this 0.4, all raised to the t power. And of course, you can test this with your table. That's one of the benefits of making a table, just to make sure that this is working correctly. Since just thinking it through by hand, we were able to figure out what it should be at the first and second seconds after the rod was plunged. But let's test our formula, and to check this, we can just plug in t equals 2, since we already know that, what that value should be for the difference in temperature. So d of 2 is just 100 multiplied by 0.4 squared, and 0.4 squared is 0.16, and you could check this with a calculator too. But 100 times 0.16 is 16 degrees Celsius, which is what we were able to figure out by just making this table by hand. So our answer makes sense, so we can plug this formula of 100 multiplied by 0.4 to the t power into our box.